Hello everyone. Um, Today to be discussing the factors that affect the rates of chemical reactions. So we're asking what makes a chemical reaction go faster or slower, and how. So we're asking what makes a chemical reaction go faster or slower, and how. That's the main question we're answering here. Some factors are mbili. To start with, temperature. Temperature has to be the most important factor. Zinazonse zinazofunika, but temperature comes first, in my opinion at least. So generally, increasing the temperature, if you increase the temperature going up, that implies that the reaction rate also goes up, or a single arrow. So increasing the temperature increases the rate of a chemical reaction. Always keep that in mind. That's the golden rule here. If you increase the temperature, you will increase the rate of the chemical reaction. Now the question is, how does that happen? So we're answering the question what. So the what bit, the temperature, that makes a chemical reaction go faster. So the higher the temperature, the faster the reaction. The lower the temperature, the slower the reaction. So now the question becomes, how does that happen? So you see, temperature gamma guera, if you increase the temperature, you increase the kinetic energy of the particles that are taking place in the chemical reaction. Sometimes you see temperature being defined as a measure of the average kinetic energy of particles. So sometimes defined as a measure of the average kinetic energy of particles in that object. So the temperature of an object is a measure of the average kinetic energy of particles in that object. So the higher the temperature, the higher the average kinetic energy. So kinetic energy is essentially the energy of motion. You see, the higher the kinetic energy, the faster the particles move. And so basically a chemical reaction, for it to happen, particles must collide. Say for example, if A reacts with B to form C, then essentially A particles will be going this way, B particles will be going that way, and eventually you have um, A smash into B, and then that somehow ends up forming C. So the faster these particles are moving, then they will be able to collide more frequently and they will be able to form C more often than not. All right. So that means if you increase the temperature, you increase the speed of these particles, you increase their kinetic energies, you make them collide faster and with more power, with more force, with more energy. And that causes them to form C faster than they normally would if there was no high temperature. Okay, so they collide faster and with enough energy to overcome the activation energy barrier. So we'll talk about that in a bit, but the activation energy, that's the minimum energy that the particles that are colliding must have for a chemical reaction to take place. If A and B are colliding with energies lower than the activation energy, no reaction takes place. So you can see that the higher the temperature, the more the kinetic energy, because they have more speed now. They move faster and they will be able to collide with enough energy to overcome the activation energy barrier. This means more molecules of A and B will be colliding with enough energy to form C. All right, so that's enough about temperature. That's enough. That's enough about temperature. So moving forward, the concentration of reactants. So once again, the general rule here is the higher the reactant concentration, implies the higher the reaction rate. Okay, so the higher the reactant concentration, the higher the rate of the chemical reaction in general. And that's the general rule, as I said. And the key thing here is probability or chance of collisions. See, we're saying for a chemical reaction to occur between A and B have to collide. They have to smash into each other to form products, say C or anything else, right? Now, if there are more molecules of A and B, then the chances or the probability of A and B running into each other to collide and smash to form C, the probability is very high. So clearly, more reactant molecules imply a higher chance or a higher probability of collision between them. Therefore, which means you increase the chance of having successful collisions, which in turn are successful reactions. Perfect. Moving forward, another factor that affects the rates of chemical reactions is the surface area of reactants. You see, if you have a solid and then you break the solid down into powder, okay, so say this is a block of solid and this is powder. This has a small surface area and this has a large surface area. So if you have a solid, a block of solid with a small surface area and you break it down, you pound it, you crush it into powder, you'll be able to get a large surface area. And so if you increase the surface area, you will have a faster chemical reaction, because in this solid you can imagine that some of the particles are not exposed because it's only the outer surface of the solid. It's only this outer surface. 1, 2, 3, 4, 5, 6, 7, and 8. This has 8 faces. This has 8 faces. It's a cube, or it's a cuboid, what have you. And so it's only these particles that are exposed that will be able to take part in the chemical reaction. But now if you break it down into a powder, right, if you crush or grind into a powder, then this powder makes sure that more particles are exposed and available for reactions, which means you have more frequent collisions between reactant molecules. Okay, perfect. For example, think about it. Say you have a block of ice that you want to melt. If you crush it into smaller blocks, for example, if you crash it into smaller blocks, these blocks, smaller blocks, these smaller blocks will melt faster compared to this huge small chunk because there is more surface area exposed to the process of melting. More of this surface area will be exposed to, for example, the heat that's supposed to do the melting. Compared to here, it's only the particles on the surfaces that will be able to take part in the melting process. Perfect. Moving forward, my favorite part, the presence of a catalyst. So a catalyst is a substance that increases the rate of a chemical reaction without itself being consumed. Of course, my definition of what they're saying, a catalyst is a substance that simply alters or changes the rate of a chemical reaction without it being consumed. By alters or changes, it means it can decrease or it might increase. But for our intents and purposes, we shall say that catalyst presence translates to increased reaction rate. That's what we're going to say. So we'll talk about reaction pathways later, but any reaction can proceed in multiple pathways. And you can think of it as one pathway has a very high resistance, which means a higher activation energy. And the catalyst is like, wait, you don't have to go through that route. You don't have to pressure yourself. You can use another way which has a much lower resistance or a much lower activation energy. So if someone says, what are catalysts? You say, catalysts are substances that increase the rates of chemical reactions without themselves being consumed in the process. Perfect. But then how do they affect the rate of a chemical reaction? They provide an alternative reaction pathway with least resistance or with lower activation energy. This means that most reactants can be able to participate. Imagine if you're at a weightlifting contest and then we're saying, okay, guys, or ladies and gentlemen, come here and lift this 100 kg barbell, for example, this thing. Like, only a few people will be able to lift this thing. So lifting, you can think of lifting as the reaction itself, right? Only say maybe there's 50 people, and then you could find that maybe only 6 people are able to lift this thing. But then if you say, okay, no worries, instead of 100 kgs, let's make it 20 kgs. Now you see that more people will be able to lift it. Say maybe 48 people might be able to lift it. Now you see that the person who says, wait, how did I spell catalyst here? This must be a Y. Must be a typo. Sorry. So at first, we had this pathway, 100 kg, with the cut. So we only had like um 6 people who were able to lift that. But now, if we reduce the weight to 20 kgs, about 48 people were able to lift it. So this person who says, okay, wait, you can do this the easy way, just 20 kgs, this person is the catalyst. Perfect. I think I spent way too much time on the catalysts. I love catalysts, so bear with me. Moving forward, for gases, number 5 only applies for gaseous reactants. So if you have gaseous reactants, if you increase the pressure, generally you're going to have a higher reaction rate. Okay, because effectively, for gases, remember, if you remember from the ideal gas law, say PV equals nRT, and then we could say P equals N over V RT, okay? And then you could see that N over V is essentially the molar concentration. So we could say pressure equals concentration of reactant. This R is going to confuse with R, so I'm just going to leave it at C R T. So what this tells you is that the pressure is directly proportional to the concentration for gases, because this is a constant, and if you keep the pressure constant, then indeed P is directly proportional to C. So for gases, higher pressure compresses the gas, and this increases the concentration of the reactant. And we have already talked about the effect of concentration here. Increasing the reactant concentration increases the reaction rate. This is exactly what we talked about. Perfect. So next time we are going to discuss how we measure reaction rates. For now, keep this in mind. Temperature is pretty much the most important factor. The concentration of reactant, yes. The surface area, we talked about having a chunk of solid, grinding it into smaller bits increases the chances of having a reactant colliding with another reactant because the surface area is very large. A catalyst offers alternative pathway with lower activation energy. For gases, you increase the pressure, you're going to compress the gas, increases concentration, and we've already seen how concentration affects the reaction rates. Perfect. So until next time, you have an amazing time.